So now with this +1 way of getting from one Boolean formula to another with the number of assignments incremented exactly by 1, what we can do is we can remove the OR operator. So thus by induction we can randomly reduce psi, which is parity Z, there exists X for all W, phi ZXW to parity Z we will make there exist into parity for all W will stay there. A new formula phi prime on Z X star W for a new Boolean formula phi prime. Okay, so we have managed to reduce these 3 quantifications into 2, parity and then for all. Also, we can remove the for all quantification by using the following property. The property is parity X for all Y fxy. This is equivalent to just negate the for all, the inner part, which is it becomes there exists Y negation of fxy. Okay, this is the negation part. Why are these two equivalent? Well, because if the inner part, this part, if this satisfying assignments, number of satisfying assignments X is odd, then for the complement of that, the negation. So if this is true odd many times, then it's also false odd many times. That's the proof. So number of satisfying assignments plus the number of unsatisfying assignments this is equal to 2 raised to n. So even. Just use this fact. Okay, so since the sum is even, if one is odd, the other is also odd. If one is even, the other is also even. So this is why these two formulas are equivalent. And so what you have achieved is parity for all. It can be replaced by parity there exist. And then again the same story, there exist by the previous proof can be reduced to parity. So by this this sequence of transformations, by these transformations. We randomly reduce to parity Z, that's the same original Z variable, then X star, W star, and a new Boolean formula phi prime prime. So Z, X star, W star, which is equivalent to psi that we started with long time back. So parity Z, parity X, not parity, there exist X for all W phi, right? So these three quantifiers we have reduced to one with some error probability that's manageable. That's what we have achieved after all these transformations. And these there exist for all, they alternate C times, right? So you can keep repeating this and the blow up will not be too much. Remember that this plus one adds new variables, but C is a constant, so it's not too bad. So since in a general psi we have C many quantifiers, we get only a polynomial blow up. In the size of the final formula using only parity. Right, so this there exists for all C many times, this ultimately becomes a single parity. Formula keeps growing up from phi to phi prime to phi prime prime and so on, but that is only a polynomial blow up because C is constant. Because remember we have been blowing up with this OR operator which was T times, and what was T? T was like N, right? N times L. So every time it's actually a polynomial blow up, but it's happening only C times. C is a constant. So C constant is important. Let's remember that. Otherwise this would not have worked. So that is why polynomial hierarchy, we are in polynomial hierarchy, not beyond. We cannot run this proof over QBF. Okay. And this means that we have actually reduced sigma C sat to parity sat. With very controlled, very small error probability. right? So this finishes our random reduction of pH to Parity-P. So pH random reduces to Parity-P, which is in P to the sharp P. So this is great, but what was our main theorem? So lemma 1 has been proved. Lemma 1 was this both-sided error reduction of pH to parity sat. So lemma 1 is done here. But is this enough for our bigger picture? So in the bigger picture, remember what we want to show is that Toda's theorem. So that pH is contained in P to the sharp P. Right? We are not yet there, because this is just a reduction to P to the sharp P. It's not showing that pH is contained in P to the sharp P. So that will only be possible if we can remove this keyword random. We have to give a deterministic polynomial time reduction. So in other words, we have to de-randomize it. So how do we de-randomize the reduction? So the idea here is this parity operator is mod 2 arithmetic. So instead of mod 2, you make it mod 2 power arithmetic. So amplify the mod 2 value to mod 2 raised to m value for a large m. Okay, so why will this de-randomize? See, so you want to go over all the random strings, all the strings in your in the space from which you are picking the random string R. So if we can show that for any R, the answer that you are getting, it's not just 0 1 mod 2, but it is actually, let's say, 0 1 mod 2 raised to m, where m is larger than the size of random bit. M is bigger than the number of random bits. Okay, then we can do a sum over. Then what will happen is you consider the sum over all R's. In this formula that you got, the formula psi, the formula value. So the sum over all the formulas that you are getting, mod 2 raised to m, if we look at this sum, then this will tell us whether phi was true or false. Will tell us whether phi is true or phi is false. Okay, that's the rough idea, that amplify this mod 2 value to a higher modulus and then take the sum over all the random strings R that the reduction is using. So essentially, when phi is true, then 2/3 of these will be, let's say, 1, the other 1/3 will be 0. So this will be large, and in the opposite case, this will be small. So this will actually be large or small. And that will tell you whether the formula is true or false. Okay, so true will map to a larger value. That's the idea. True will map to large, false will map to small, because of this 1/3, 2/3 that we have ensured. So this will need a kind of algebraic lemma. So this lift is algebraic and is inspired from an algebraic lemma called Hensel lifting. So what is this lifting lemma? Lemma 2 So this says that if psi is a Boolean formula, and m is natural number, then there exists a polytime Turing machine T such that it will transform psi to phi, this will be output of T given the input instance psi and m. It's a Boolean formula satisfying the following. So if the number of satisfying assignments of psi was odd, so 1, then it will lift to -1. In a much higher modulus, which is 2 raised to m plus 1. Okay, so -1 and 1 are the same mod 2, but when you go to higher modulus like mod 4, 1 and -1 are different. But the thing remains that I mean, this intuition that I gave before, that look at the sum will be either large or small in magnitude, that will remain the same, because when you look at number of satisfying assignments even, this lift will actually be congruent to 0. Okay, this is important. So 0, 1 lifts respectively to 0, -1. Okay, so there is this gap. So when you take the sum of instances for different hours, you will see the gap. The gap will get this gap actually is getting amplified. This is why this lifting lemma will directly Okay, let's do the proof of this first. And the proof will then almost directly give you Toda's theorem. So the proof is, as always, it will be inductive. And induction will be on M. Okay, so first you have to learn how to go from mod 2 to mod 4. That's the point. So build phi iteratively using operations plus and multiplication. So we had defined plus 1 before. Now we will define plus more generally. We can add actually 2 formulas, and we'll also define multiplication, which is quite easy. This will just be AND. So this you can think of as induction on M. This will be like induction on M, but not exactly. So so formulas fx and gy give new formulas as follows. So f plus g will be, okay, f plus g will be x, just one new variable will be added. What you do is, for u equal to 0, look at assignments, satisfying assignments of f. Otherwise, those of g. Okay, so this intuitively adds the number of satisfying assignments of f and g. Okay, it basically branches off. U equal to 0 goes to f, u equal to 1 goes to g. So they get added. While in multiplication, what you do is, here you keep the variables separate because you want product. So for every satisfying assignment of x, you can pick one satisfying assignment y, respectively that of fg, and you can see that the number of satisfying assignments of f multiplied by g is product. Okay, so it is now easy to see. It's easy to see that the number of satisfying assignments of f plus g Boolean formula is sum and that of f star g is product. Okay, so as the intention was, that is what we have implemented. Sum of satisfying assignments or product of satisfying assignments. And now we can go from mod 2 to mod 4. From psi, we will build a new formula. So initialize the iterative process with the phi 0 defined to be psi. Okay, phi 0 is what we were given in the input, that's psi, and now we can define phi 1 using this addition multiplication, so that phi 1 will have number of satisfying assignments -1 respectively 0 mod 2 square. okay, m equal to 1 case. So this we'll do next time.